Hi, and welcome back to Module 8.2. This is really part 2 of 8.2, and we're going to talk about the topic of a binomial distribution. When we talk about a binomial distribution, we're really talking about a special formula for finding discrete probabilities when we have problems that meet some very specific qualifications, excuse me. The qualifications must be met in order for this formula really to work for that given situation. Number one, we have to have a decided on fixed number of trials. So certain problems that we've looked at, for example, if we're playing a blackjack game and we're going to stop as soon as we lose or as soon as we win and walk away, then we don't have a fixed number of trials because the sample space could have one trial. If we played one game and won, we could have two trials. If we played two games, loss and then a win. So we have to have a set number of trials under which we're going to function. Number two, our trials have to be independent, meaning the probabilities are not changing as we move from trial to trial. And we can only have two possible outcomes, not four, not six, but two. Usually we deem one outcome a success and the second one we deem as a failure. We usually label the success as P and then the failure would be its complement or 1 minus P. So if my probability of success is 60%, 1 minus 0.6 would be 0.4, so we have a 40% probability of failure. So you're going to see this 1 minus P show up, but always keep in mind that 1 minus P is something you can easily do without actually having to type it out, right? Because it's just a complement, whatever these two would add up to give me 1. So sometimes we simplify some of these formulas just by putting an F in there instead of 1 minus P. But we do keep in mind that it is a complement. And then our random variable X is going to be always the number of successes, and N is going to represent the number of trials that we have. The types of situations where we have the independence, fixed number of trials, etc. would be, for example, flipping of a coin. All of those trials would be independent. We could decide how many times we're going to flip it ahead of time. There's only two possible outcomes, a success and a failure, and we decide which we're going to call a success. And yeah, so clinical trials also. Either they get well or they don't. So we call that a success or a failure. And also defective products in a sample line. I'm sorry, defective samples in a product line. Yeah, so either they're defective or they're not defective. So we have two trials. Each item, each sample is independent of the other ones. But before we get to the actual formula for the binomial distribution, we need to look at some principles that we use generally in statistics. And these principles help us to count. As you recall, one of the things we need to know in order to find probability is to know how many outcomes are possible. In other words, how many items are in my sample space. And so the fundamental counting principle is something we can use for us to come up with that information. We don't necessarily have to have all of the outcomes written out. As long as we know how many there are, that's all we really need for our probability formula. So the fundamental counting principle says that for a sequence of n experiments or trials, if the first trial has k number of outcomes, and the second one has k2 number of outcomes, and so on, the total number of possible outcomes is going to be the product of the number of outcomes per trial or experiment. In other words, for example, if we were rolling a die, you remember that there's 6 outcomes possible. But if we roll a second die, that second die also has 6 possible outcomes. And so if we wanted to count the number of total possible outcomes for rolling 2 die, we would multiply those two numbers together, 6 times 6, And 36 is that understanded number of outcomes that we've looked at it several times. Let's apply this in another area. For example, we can use this fundamental counting principle if we're wanting to know how many area codes are possible. If we have three numbers in our area code and the first one cannot be a zero. Given that, the number of area codes, we have 3 digits in our code. The first one is limited and it cannot be a zero. So that leaves us with 9 other possible fill-ins for this space. Then we have 10 possible fill-ins for the next space, 10 possible fill-ins for the next space. And so what we see is there is 900 different area codes possible with a 3-digit number where the first number cannot be a zero. This also is the fundamental counting principle here at work. Another function mathematical function operation that we're going to look at is called a factorial. This is an important mathematical expression using counting when there are fewer and fewer possibilities upon each successive trial. And it's a very exciting operation in that it's so exciting we use an explanation point to represent it. And here's what the explanation point means. If I have a number and we're taking the factorial of that number, the result is that number times 1 minus that number times 2 minus that number, all the way down until our numbers go to 1. So for example, 4 factorial, we have 4 times 3 times 2 times 1, so 24. 5 factorial, 5, 4, 3, 2, 1, multiplied together give me 120. So we can see that these numbers begin to get very large very quickly. In fact, let's go ahead and calculate what would be the factorial of 10 factorial. So here's how you can do it with your calculator. We don't have to do this by hand. It would get very tedious after a while. But under your math button, which is on the side of your calculator, under alpha, and I'm going to pull up my calculator here so I can demonstrate for you. Okay, so here's my calculator, and I'm going to clear out this screen. Just get a blank screen, and I'm going to put in the number 10. And if I go to the math function, you look across the top there, look for PROB. Of course, you know what that means. That's probability. So go over that, and you'll see choice number 4 has that little explanation point. So I'm just going to hit 4 here, and it inserts that explanation point. Notice that I also had to, at first, put in the number I was going to find the factorial of first, and then we hit enter. And we can see that 10, by the time we get to 10, we are at 3,628,800 is 10 factorial. So these numbers get exponentially large very quickly. All right. So going back to here, another thing I wanted to throw in here, and here's the instructions on how to get to the factorial. We do have a special definition for 0. 0 obviously falls less than 1, right? So it kind of falls outside of this definition that we've created for n, because these numbers go all the way down until we reach 1, and then we stop. And of course, anything times 0 is equal to 0. But what we find is we actually end up with a couple of formulas where 0 factorial ends up being the result in the denominator part of our formula, which is a problem. We can never have 0 in the denominator part. But just as a side, sometimes we end up with that. So we put a special definition for 0 factorial that it always is equal to 1. Though there's no isn't necessarily a meaning behind that. It's just something we decided. Okay, so another function that we want to explore, which builds on this whole factorial, in fact, it uses the factorial. Within it, it's called a combination function. It's a way for us to figure out how many ways something can be arranged. Now, combinations specifically give us the number of ways that we can arrange in our distinct objects from indistinct objects when order is not important. So we're not considering order to be uh, important. And we'll look more at what that means here in the future. Now, this is something that you can do on your calculator, so you're not going to be required to do this by hand. But the idea here I wanted to show is that n represents the number of trials or the number of objects that you have, and R represents how many we're going to select from those um, n different objects. And so we have this formula up here. And here's an example of where we might use the combination formula. In a cafeteria, Joe can choose 3 different vegetables from a choice of 8. How many different ways can his plate be filled? So again, this is a way for us to count the number of ways that we could get 3 unique objects on a plate, 3 unique vegetables on a plate. Notice that once those vegetables go onto that plate, there's no real order to them. So the fact that I scooped out the carrots, and then I scooped out the peas, and then I scooped out the broccoli is the same plate of vegetables as if I had taken broccoli first, carrot second, and peas third. Right? So we would not want to count them as separate counts, like different plates. It would still be the same plate of 3 vegetables. And so that's what we mean by order is not important. We would not treat those 3 things differently. All right, so putting these numbers into this formula, and I'm going to show you again how to do this on your calculators here in a minute, we find that there are 56 different combinations of vegetables, where the 3 vegetables on the plate would be different. Now, this formula is an important part of the binomial distribution formula that we're about to look at here in a minute. But before we move into that, I want to show you how to do NCR on your calculator. And so let me give you another example. Let's say that we have a committee. So we have a class of 30 people, right? And I want to make a committee of 3 people to represent those 30 people in the class. Now, because I'm forming a committee, there's no real order to those individuals. They're all on the same committee, right? So if I pick John, then Judy, then Jeff, that's going to be the same group of people as Jeff, Judy, John. So we would not want to count them as separate counts, those 3 people. If those 3 people are chosen, that's one count. Okay, so order is not important because I'm putting them on a committee. Now, if I was choosing a president, a vice president, and a secretary from those 30 people, then the positions that they're in would make a difference if I rearranged them into different positions. And so their order would be important. Okay. So on your calculators, again, pull those up. And the first thing we're going to type is the number of trials that we have. And the number of trials that we have in this case, we have a class of 30 people. I'm going to try to find my calculator here. We have a class of 30 people. And with my 30 people, I'm going to type that in first. I know that I'm dealing with a sample of 30. So just like before you had to type 10 first, you need to type your N first for the NCR. Now we're going to go to math again and toggle over to probability. And you can actually see there, NCR is the 3rd choice down the list. So I'm going to go ahead and highlight that, or you can highlight it and hit enter, or you can just hit 3. And so you can see it substituted 30 in for N. And now I'm going to put 3, because I'm forming committees of 3 people from the 30. And my question is, how many unique committees could I make from those 30 people? We hit enter, and we see that there are 4,060 unique committees that I could make from those 30 people. So quite a few. Very interesting. All right. Moving back to our presentation, let's go ahead and get back into here. Go to the next slide. We're going to take you through an example that is going to help us lead into what the probability formula does for us, what the binomial distribution formula does for us. So here's an example. We're tossing a coin 4 times, and we want to know what is the probability of getting exactly one head. Now, in the multiplication rule that we looked at, where we know that that applies when we have one event followed by another. And so this is an example of that type of situation where we're tossing a coin 4 times. Every time we toss it, there's a 50% probability it's going to be a head. But what we want to know is what's the probability that of those 4 tosses, we only get exactly one head, which means a head and 3 tails. Now, whenever I find the probability of, say, for example, let me pull it up, heads on the first one, tails, tails, tails. So this is going to be 50%, 50%, 50%, 50%. So 0.5 to the 4th power really is what this particular probability is. 5 to the 4th, 0.5 to the 4th power is really the probability of specifically getting this group in this particular order. So in other words, not just one head and 3 tails, but heads first, followed exactly by 3 tails. So there's 4 different ways that I can actually end up with one head and 3 tails. I could get heads on the first toss, heads on the second, heads on the third, and heads on the fourth. Each one of these combinations we would consider a success, and they all share the same probability because it's 50, 50, 50, 50. Or in other words, each one of those has a probability of 0.0625 attached to it. So if I want to know that without order being considered of how I could get one head and 3 tails in any order, we would want to find the probability of each of these because each of these would be considered a success. And the or is here because we could either get this or that or that or that. All of these considered a success. You know that or relates to plus, so I really want to take that probability and add it 4 times. In other words, multiply this by 4, and we get our probability, which is 0.25. Now, 0.25 is the probability of this outcome, and this is something that we could do on our own, because there's a limited number of tosses. Let's see how the binomial distribution formula, which is right here, helps us to do this more quickly and with less effort on our part. Because trying to figure out all the different ways it can happen can sometimes be challenging. All right, now I know this looks intimidating, but let's go through and take a look at it before you get too intimidated. First of all, we're finding probability, so over here we're just saying the probability that my random value of x will equal, and then we put a little x here in this formula because this is representing the specific number of successes we wish to see in our particular problem that we're calculating. Then we take the NCX. So notice that this here is going to be the same number as we have as far as successes. So x is my number of successes. N is my number of trials. So we're flipping our coin, or we're picking so many items from the population, what have you. And then P is our probability of success. So here you can see P is going to be our probability, and we're going to raise it to the power of the number of successes we want. So, and we'll see this in an example. And then 1 minus P represents the failures, and we're going to raise it to the number of failures we expect to see. In other words, the number of trials minus the number of successes we expect to have. So let's look at the previous problem that we just did and see how the binomial distribution can help us calculate this. So first of all, we'll identify our values. We have 4 tosses of the coin, so n is equal to 4. We expect to get 1 head, so we're dubbing heads a success, and we know the probability of success is 50%. So putting these into the formula, we have 4 trials, 1 success. What this is going to do is this is going to give me the number of ways I could have 3 tails and 1 head. So I don't have to write them all out and try to figure out the number of ways. And then over here, what we eventually come up with is the probability for each one of those specific outcomes. If you recall on that previous slide, each probability had, or each combination of 3 heads and 1 tail, or vice versa, sorry, 1 head and 3 tails, each one of those had the same probability, 0.0625. Well, this is going to calculate this for us, and we'll see that here. We have 4, because there's 4 ways it can happen, multiplied by 0.5 to the first times 0.5 to the third, so that's basically 0.5 to the 4th power. And this gives us that same probability we just found, which is 25%. Where this really comes in handy is when we have a large number of trials and maybe not just 1 success. So here we're just going to throw out some bigger numbers here. We're going to have 10 coin tosses instead of just 4, and the probability of getting 6 heads. Now, if I were to try to write out the sample space, all the possible outcomes for 10 tosses of the coin, going back to my fundamental counting principle, that's going to be 2 to the 10th power. 2 times 2 times 2, because each time I flip the coin, there are 2 outcomes possible. So 2 multiplied by itself 10 times, or 2 to the 10th power, would give me 1,024 different possible items in my sample space. I'm trying to figure out how many ways I could have 6 heads and 4 tails in every particular order is going to be a gargantuan task that we don't want to do. So this is where the binomial distribution is going to help us. We have 6 heads. We're considering heads a success. 10 trials with 6 successes. This is, again, going to count the number of ways that that can happen. And then we're going to multiply this by 0.5 to the 6th. This also ends up being my probability of failure. In other words, getting a tail is 1 minus 0.5, so 0.5 as well, raised to the number of failures I expect to see, or the number of tails I expect to see, which would be 10 minus 6, 4. So again, this is 0.5 to the 6th power times 0.5 to the 4th power, in other words, 0.5 to the 10th power. And we could put these together if we wanted to, just because they happen to have the same base. They're both 0.5. So we could just express that as 0.5 to the 10th power. And 10 combinations of 6, that's something we can type directly into our calculator. In fact, let's go ahead and bring that up. To type this in, I'm going to go 10 first. I got to put the number of trials I have. We're going to go to math and then probability. Oops, a little bit too far there. And then we're going to go to choice number 3, the NCR. See, it filled in 10 for my number of trials. And now I'm going to put the number of successes I want, which is 6. All right. And then we're going to multiply this. Oops, let's get it out of the subscript there. Delete that. Go over. We're going to multiply this by 0.5 to the 6th power times 0.5 to the 4th, which is 0.5 to the 10th. So I'm just going to go ahead and put that in there, shorten this up a little bit, hit enter. We see 0.2050, or about 20.5%. Okay. Now what I'm going to do is have you get your calculator out, and I would like for you to calculate this probability. And we're not doing a real world scenario here, we're just giving you the numbers. So using a binomial distribution with 10 trials, probability of 20%. And so what does that make my probability of failure? Yes, you're correct. It makes it 80%, right? So we're going to have this as my p. 1 minus p is 0.8. I would just put that in your calculator. And then we want 6 successes, kind of like we had on the previous one, except now my probability is a little bit different. Go ahead and see if you can calculate that. Just go ahead and pause the recording right now. All right, and you should get 0.0055. And I'm going to go ahead and pull up the calculator here and demonstrate how we would do this. And we have 10 trials, so 10. I'm going to go to my math, go to probability, and we want choice number 3 there. With 6 successes. I'm going to hit the arrow button. Some of you won't have to do that, but I do on this calculator. My probability of success was 0.2. So I'm going to put 0.2. I'm going to raise that to the number of successes that I'm after, which is 6. In other words, 2 multiplied by itself 6 times. Then we figure out what the probability would failure be, which is the complement of 0.2 there. So don't do the whole 1 minus 0.2, just put 0.8. And then we're going to raise this to the 4th power, the n minus x. So if you'll notice, the powers here end up adding up to the number of trials, and however many successes I want is my first power because we put the probability of success first, probability of failure, and then whatever we would need to get, how many failures you would need to get to have 10 trials. We hit enter, we see 0.0055. So there's about a 0.5% probability that I would have 6 successes in 10 trials with a probability of 0.2. You can use your PowerPoints to calculate this as well. I'm going to move on to the next slide. You can hit pause and do that and check it with your key to see how you do there. Let's see how this can be applied into a real-world experiment. All right, so here we have quality control expert at a large factory estimates that 10% of the batteries produced are defective. If he takes a sample of 15 batteries, what is the probability that oops, sorry, got you to the wrong screen here. Let's go back. So let's go back and reread this. A quality control experiment at a large factory estimates that 10% of all batteries produced are defective. If he takes a sample of 15 batteries, what is the probability that exactly 2 are defective? All right. So I'm going to go ahead and write out how we're going to set this up. In this case, the number of trials we have is our 15 batteries that we're selecting. So we have 15 combinations, and I can't make that small, so just know that that's the end. 15 combinations, and we're going to call this time our successes as picking a defective battery. So I have 15 combinations of 2. The probability of success, which we've defined as picking a defective battery, is 10%. We're going to put 0.10, and we're going to raise that to the 2nd power, because that's how many defective batteries I expect to see. And then my probability of failure of getting a non-defective battery is 90%, but we're going to raise that to the remaining 13, so to the 13th power. Put that into our calculators. And what do you get? I'm going to give you a minute to come up with that. should see 0.2669. That is our probability. If we put it as a percentage, that would be 26.69. So almost a quarter of a probability, or a quarter of a 25% chance, almost, a little bit more than 25% chance. Now here it gets a little more tricky. Here we want to know what's the probability that at most two are defective. Well, at most there is something a little bit different. At most suggests that there are multiple ways to be successful, right? In this case, we would say the probability, we would have to set this up as an inequality. As far as my successes go, the number of x's, at most 2 would mean that we would have less than or equal to 2 defects. So this means many different possible outcomes. For example, a probability that x equals 0 would be one possibility. We could also have one defect, and that would be included in that. And then we could also have 2 because it's less than or equal to 2. And in fact, at most always translates into a less than or equal to, ironically, because we think most, we think more, but most gives us an upper limit. Like if I said you can have at most 3 absences in this class and still pass, right? So 3, you know, is the highest number you can get. Where I say you have to have at least 70% to move on, you know, 70% is the bottom, and we can go up from there. So at least translates into greater than or equal to. At any rate, our binomial distribution formula only works for equals. Doesn't do the inequality like we have here. And so therefore we have to figure out all of these individually. We have to do the binomial distribution formula with them. So what we have to do here is find the probability that we have no successes. So we have 15 trials, so 15 combinations with 0 successes, multiplied by the probability of success. I'll have to put a space there. Probability of success in this case, again, is 0.10. We're going to raise that to the 0 power because we don't want any successes. So raised to the 0. And then multiply by the probability of failure, which is getting a non-defective. We're going to raise that to the 15th power, because we basically want to find this will give me the number of ways that I can, or what the probability is that none of the batteries are defective. We have 0 defective batteries and 15 good batteries. To this, we're also going to add the probability that x is equal to 1. In other words, we have 15 combinations, and I would recommend as you're doing this with one success, as you're doing this, to figure each one of these out individually, write it underneath. That way you can keep track of these. We're going to raise that to the first power and multiply by 0.9, risen to the 14th power. And notice my powers here, 14 and 1, add up to my total number of trials, which is 15. And then lastly, we're going to find the probability that x is equal to 2, but we already found that up above. And we don't have to retype all that out. I'm just going to put 0.2669. Go ahead and see if you can figure out this probability for each one of these. Let's do each one first. Go ahead and pause it if you wish and calculate these out. I'm just going to jump right into here. So for the first one, you should get 0.2059 if we round it to 4 decimal places. And for the second, with one success, you should get 0.3431. And of course, for the last one, we already found that. So that's equal to 0.2669. And if we add up all of these, we get and I'm typing these into my calculator as well. Oops, gotta try that again. This is what I got. I'm typing it in pretty fast, so I'm hoping it's correct. But I get 0.8159. This is the probability of having at most 2 defective items in my line. So this concludes our lesson over binomial distributions. What I recommend is you write these out on paper. I know it appears to be, but if you do these separately, a lot of times these questions build on each other, and you can use a previous entry, like we did here, where you don't have to recalculate the whole thing. But watch for these keywords at most and at least, and write out what that means in terms of probability and all that, and really keep yourself organized and write out what that includes. If it just says greater, then it's greater. And the other thing you want to watch for is the opportunity to use the complement rule. Because the complement rule, if you recall, whenever we see the term at least one is always the complement of none. That is correct. So watch for that opportunity, because a lot of times you don't want to have to write out every possibility. Sometimes it's easier just to take the complement, and usually you might have one or two instead of 10 or 15 different calculations to do. That comes out to our to the end of this lesson. We'll see you in 8.3.